Ever try to read a book by holding it right up against your nose? The letters instantly blur into an unreadable smudge. That blur marks a biological threshold called the least distance of distinct vision. For a healthy eye, this boundary sits at exactly 25 centimeters. There is a second physical limit to our periphery. If an object moves far enough to the side, it vanishes from our field of view entirely. This defines the maximum angle of vision, which caps out at approximately 60 degrees. These specific limits confirm that human vision is a physical system, governed by the rigid laws of geometry. To generate an image, light must bounce off an object, enter the eye, and strike a highly specific target. That target is the retina. In a standard eye, it sits at a fixed, unchangeable distance of exactly 2.5 centimeters behind the lens. The problem is that the external world is made of objects at constantly shifting distances, yet our internal projection screen is perfectly static. This creates a complex optical discrepancy that our biology must solve in real time just to keep reality in focus. Light passes through the cornea and slips through the pupil, entering a variable aperture that regulates the incoming signal. From there, it hits the crystalline lens. But unlike the rigid glass found in a camera, this biological lens is flexible. Through a process called accommodation, internal ciliary muscles physically morph the shape of the lens to adjust its focal power. When you look at a distant object, these muscles relax, the lens flattens, creating a maximum focal length of 2.5 centimeters that lands perfectly on the retina. To see something close up, the muscles contract and the lens bulges, shortening the focal length to 2.27 centimeters while keeping the image anchored on that back wall. This rapid, physical reshaping of the lens is the evolutionary hardware solution that keeps our perception of a dynamic world sharp. However, this organic hardware can fail due to genetics or age, resulting in structural defects that the eye cannot correct on its own. The first major glitch is myopia, or nearsightedness. In a myopic eye, the system is mechanically misaligned, causing incoming light to converge much too early. As this diagram shows, the image is projected in the middle of the eye before it ever hits the retina, leaving anything in the distance as a blur. Myopia effectively collapses a person's far point, drastically shrinking the scale of their functional visual universe. The opposite mechanical failure is hypermetropia, commonly known as farsightedness. Here, the eye's minimum focal length degrades, extending past the necessary 2.27 centimeter threshold. The light rays strike the retina before they can form a point, theoretically projecting the sharpest version of the image into the space behind the eyeball. Many people also face presbyopia as they age, where the lens hardens and the ciliary muscles weaken, making it impossible to achieve those short focal lengths. When this biological hardware fails, we become isolated from our surroundings unless we can find a way to mathematically intervene. Since we cannot easily replace the biological lens, we have to hack the trajectory of light before it ever enters the eye. Corrective lenses do exactly this, pre-bending light rays using the predictable physics of refraction. A concave lens spreads light out to fix the early convergence of myopia, while a convex shape pre-focuses light to compensate for hypermetropia. For complex aging defects like presbyopia, engineers often combine both concave and convex corrections into a single piece of hardware, known as bifocals. The strength of this intervention is measured in diopters, a standard unit that determines exactly how much corrective power is required. Through calculated mathematics, we can patch these biological failures and restore a sharp connection to the world. Shifting focus from biology to physics, these same refractive principles allow us to probe the nature of light itself. This is the purpose of the prism. Its angled surfaces are designed to purposely deviate a ray of light, bending it away from its original path. By tracking this path through the glass, scientists can calculate the exact angle of deviation. Calculating this deviation reveals a material's refractive index, the precise measurement of how different mediums alter the speed and path of light. By mastering this invisible geometry, we gain the mathematical framework required to measure and map the physical universe.